Then I'd like to go ahead and start today's webinar. This is the second series that we have with the NCS Center, and our first speaker is Felix Feldmann. So I will give it to you and let you continue. Thanks.
Thank you. And thank you, Lisa, for inviting me today here to give me or us once more the chance to present our work on IORSim. And today I'll talk about the IORSim development within the NCS 2030 Center. Before I start, IORSim is a joint collaboration or development of NORCE, IFA, and the University of Stavanger. And it was previously developed as part of the IOR Center, and now again it's part of the NCS 2030 Center. A short introduction. If I could change. There we go. Yeah, a short summary of the IORSim software. An overview. What is IORSim? It is a geochemical solver that is focusing on complex reservoir systems. And since IORSim is focusing on, again, complex reservoir systems with long decades of injection and production histories, IORSim is using a standard reservoir flow simulation program.
Men vi var jo kjempestrenge. Så det var liksom vanskelig å stoppe.
Such as Eclipse or Intersect to realize the flow calculation, and then IORSim is adding the geochemical interactions to the reservoir model. IORSim comes with two dedicated simulation modes. Initially, the unidirectional forward mode. So in this case, Eclipse or any flow simulator is finishing the entire flow calculation up to 50 or even more years of injection and production history of a reservoir. And then after completing the flow simulation, IORSim is detecting the chemical species and is calculating the geochemical reactions. And this can be of interest, for instance, to see the impact of ion composition or injection fluids on mineral composition inside the reservoir. And then secondly, we have the bidirectional coupling mode, the backward mode. In this case, the host simulator Eclipse, or these days or today Intersect, is communicating with IORSim at each time step. So we have this Python control script that is controlling the communication between Eclipse and IORSim. And then after one time step of flow calculation in Eclipse, IORSim is again detecting the chemical species. And now if the geochemical reaction are interfering with the global fluid flow, then IORSim is calculating updated relative permeabilities or capillary pressure curves to change the global fluid flow in the host simulator. And then very quickly, briefly, the key features of IORSim. Maybe the most important innovation is the topological sorting, and that is part of the IORSim software. So instead of solving all geochemical reactions simultaneously, IORSim is decrypting the reservoir fluid flow, and it's aligning the cells along flow direction, and then IORSim can solve the geochemical reactions subsequently as iterative 1D problems. And by applying this trick, we can significantly improve numerical stability and reduce computation times. In addition to the topological sorting, IORSim offers implicit, explicit, and adaptive species transport calculations. We have grid refinement, a grid refinement option in IORSim, and to reduce numerical dispersion. And IORSim also offers splay tree calculation. So old solutions can be reused in case the solver is encountering chemical equilibriums that have been encountered before. IORSim can reuse the old solutions and reduce the computation times. And in case of many chemical components, we can also use basis swapping to reduce the number of unknowns. IORSim, or the coupling of Eclipse and IORSim, has been demonstrated on the Snorre field, which is now submitted to the SBE journal. It should be hopefully published soon. And then we have a second paper where the mathematical concept is introduced in detail and applied on the ecofisk field, and that should be hopefully soon published in Transport and Porous Media. Well, but now I'll come to the development of IORSim within the NCS Center. At the moment, we are mainly developing a near-Weilbore model. Yeah, so what are the challenges of near-Weilbore modeling? Well, if you look at the Weilbore and the near-Weilbore zone, obviously there's a shift in flow regime. So we have the transient multiphase flow inside the Weilbore, and then we have the flow inside the porous media. And typically, the porous media here in the near-Weilbore vicinity is highly heterogeneous due to Weilbore damage or formation damage. And we also have scale differences. So if we compare the size of a Weilbore to a reservoir, then the Weilbore is quite or very small compared to the huge reservoir. So ideally, we would need to do some grid refinement here to better represent the flow around the Weilbore. And this can quickly lead to computational problems. So the standard approach in Eclipse is that the inflow and outflow is controlled by well connections and transmissibilities in the easiest case, at least. And then if we look at the typical grid size, this is taken from the Snorre field. In this case, it's already a smaller grid block size, but nevertheless, 30 times 30 times 1.5 meter here, the typical grid block size. And then if we want to simulate geochemical reactions, then we encounter problems with the current implementation. So from the Snorre water diversion field pilot, for instance, we what we saw there is that sodium silicate was injected into the formation, into the highly permeable thief zone. So sodium silicate and highly desalinated seawater was injected. But then what happened is that during the injection, there was a problem with the desalination plant, and the injection stopped. And then the pressure reduced, and formation water was imbibing from the lower zone into the thief zone, and it was mixing with the injected sodium silicate inside the thief zone. And then with the conventional grid size and conventional implementation, no. So what happened is that due to this formation water influx, we had sodium silicate precipitation plugging of the near Weilbore zone. But with the standard approach or implementation standard grid size, the volume of the imbibing formation water was not high enough to, in proportion to the grid size or grid block size, to exceed the threshold concentration to obtain sodium silicate plugging in our model. So that's one possibility, and we saw that we need to improve or need to have ideally a dynamic and improved coupling of the near Weilbore and Weilbore zone to simulate such geochemical reactions. And this is what is mainly IFA at the moment working on, Jan Sagen and Børre Antonsen. So they started to implement or code add fluid solver for the Weilbore to IORSim. So we have now a drift flux multiphase model in place that works well for, or that at the moment works for steady state flow. And once this is completed, we will have an improved inflow and outflow computation. And we will be able to look, for instance, into the wave behavior in horizontal undulating wells. And we can better consider the influence of well geometry on production and flow behavior. And we are also specifically interested in simulating inflow control devices, ICDs and AICDs. And at the moment, we are working on now coupling this wellbore solver to the porous media solver. And the coupling design is in place and has already partially coded. Yeah, so this is the update on the near wellbore model that we're developing. And moreover, we're working on preparing IORSim to the latest reservoir generation, which is Intersect, Schlumberger Intersect. So now we want to, instead of using Eclipse, we want to use Intersect. And to do so, we needed to change some source code here in IORSim. And yeah, so this is working fine now for forward mode. So we can add geochemical reactions to Intersect models. And just to give you an idea, maybe how this Python control script looks, I have a slide here. So this is the interface version. So the user can now select between Intersect and Eclipse, the IORSim simulation mode, either forward or backward mode. And the user can start and stop the simulation. And we have a live plotting here in the interface. So during the simulation, the different species and well parameters are plotted and updated. And there's also a display on time estimate and so on. And in addition to the interface, we have a Python module for users that prefer to use Python scripting. Then IORSim can be imported via a module in Python and Jupyter Notebook or whatever is preferred by the user. Yeah, so this is the latest development here. And now we will move to future IORSim development ideas, particularly H2S and CO2 modeling. So in this case, we will now look into microbiological activity that we would like to add or have already added to IORSim, and we would like to look into reservoir souring. So once sulfate-rich seawater is introduced into a formation, sulfate-reducing bacteria usually consume the sulfate and produce H2S. And this leads to a souring of the oil field, or in general to the formation. And then we will have corrosion of the infrastructure inside the reservoir and also in the, upstream infrastructure. And this will lead also to scaling issues. There are different types of bacteria. Depending on the type, the population will peak as a function of temperature up to 110, 100 degrees Celsius. So that's the first parameter that needs to be considered when simulating the bacteria activity. And then we have the metabolism. So in this case, the bacteria are believed to take sulfate or use sulfate as electron acceptor and organic material as electron donator, and then H2S is generated. And I have now implemented the first attempt in IORSim, where the bacteria population or the growth of the bacteria population mainly depends on the sulfate concentration inside the water phase. And then we have a decay constant here. And then we can link the degradation of the sulfate to the chemical species balance. And I have used now the NORCE field, which is provided as a open source Eclipse Intersect and OPM file with 10 years of production and injection history, or 9 years history. And this open source reservoir model has 36 wells. And yeah, just to give you an idea what is possible in IORSim, I'm now simplified the activity of sulfate-reducing bacteria on the reservoir performance. So we have some seawater injection wells up here. Sulfate is injected as part of the seawater. And now with the delay, we do see H2S generation around the injection wells. And we have a production well down here. And now in 2005, H2S is breaking through. And yeah, so and H2S is produced. Yeah, so that's one possibility in IORSim. What we would like to look into in future in more detail. So we would need to add the temperature impact and so on, and also the partitioning of H2S into the different phases, into the oil phase, for instance. And then the second idea is to look into the impact of CO2 injection on mineralogy. So if CO2 is injected into a formation, then the CO2 will dissolve inside the water, formation water, and the pH value will change. It will become more stronger acid. And then we will have mineral dissolution. For instance, feldspar might be dissolved. Or obviously, if we talk about carbonates, then calcite will tend to be dissolved by the higher pH value. And there are further challenges contributed to CO2 injection. So reaction with organic material could happen, caprock integrity, and scale formation. Yeah, so we also started briefly to look into this in IORSim. So the sorting algorithm that I was introducing or briefly talking about in one of the introduction slides was initially only able to consider species inside the water phase, but we are now extending this, or have extended this, to the oil and gas phase. So that's one condition for simulating CO2 injection using IORSim. And we will use the partitioning tracer module as a starting point to simulate or compute the partitioning of CO2 into the different phases. And another test case implemented again on the NORCE field. In this case, I know it's a sandstone reservoir, but let's just assume it's now a carbonate reservoir, a calcite reservoir. And in this case, I'm again injecting seawater, so I'm not yet injecting CO2. But we will now see, nevertheless, once we inject the sulfate-rich and magnesium-rich injection fluid, we do see the impact on mineralogy inside the formation. So in this case, now magnesite is precipitating around the injection wells, and also anhydrite is precipitating. And if we again look at the produced water chemistry here in the production well, now if the geochemical solver is enabled and we have magnesite precipitation, then obviously the produced magnesite concentration will be lowered compared to a purely non-reactive ion transport, simply as magnesite is precipitating here. And I think that's already my update for today. So yeah, this is what we're working on at the moment in as part of the NCS project, the near-wellbore modeling. We have coupled IORSim successfully to Intersect. We have updated the IORSim GUI, and these are two ideas for future development.
Thank you very much. That was very interesting.